Welcome to the lecture on light given within the course Computer Graphics at KAUST. So far, in computer graphics, we have been dealing with light in a very simplified form. Light is one of the key elements of the scenes which we are describing in computer graphics because we define the scene essentially through certain camera which forms the eye, which looks at a particular scene, which are formed by various objects, and these objects are illuminated by a certain light. In our previous equations, which we were using for illumination, the light was either just one simple definition of intensity. Maybe it was decomposed into two lights, one light which would be an ambient light with its own intensity, and another light which is more of a directional type. Then we have been also defining a light with its various color components. In previous examples, we have been using, maybe without even knowing, the RGB color space, where for each component, R, G, and B, we had a different light intensity, different sort of scaling factor, if you like, or component of that intensity. How much is the light formed by this particular wavelength? So the R would stand for wavelengths of red light, G would be standing for wavelengths of green light, and B will be standing for the wavelengths of blue light. From the physical perspective, light is an electromagnetic radiation, and the visible spectrum of the light is an electromagnetic radiation of a certain interval of wavelengths. So, and outside these wavelengths, we cannot really perceive the electromagnetic radiation as visible light. For example, we could have as electromagnetic radiation X-ray radiation. And this form of light, if you like, we will not perceive as a sensation of our eye neural system, but we might perceive it in a different way. So the light is therefore defined as some wavelength which defines the color of that light, and it is from the perspective of physics, it is carried by an energy transporter called photon. And this photon carries the light energy and travels with this energy in a certain direction, can be at a particular time at a certain position, and this photon is radiating under a certain wavelength. And as I said, certain wavelengths we can see as light, and certain wavelengths we cannot perceive as light. These wavelengths can be defined as the speed of light constant and the frequency of this electromagnetic radiation. And this frequency needs to be within a certain range to become visible. How can we quantify the energy which is carried by a single photon? For that, we can calculate it by a multiplication of the photon's own frequency and the so-called Planck's constant, which is defined here, which defines what is the energy of entity of that one photon scaled by its own frequency. So if we combine the previous equation with this new equation, here we have our definition of our energy based on the speed of light, the Planck constant, and the wavelength. Now, the light, as we know it also, and we use it already, is an additive phenomenon. So we can add various light sources and we will just add the illumination on the top of each other. Therefore, we can also sum up the amount of the light energy from a single photon through all the photons which are sort of considered in our scene to form the total energy of a particular light source. From our high school physics lectures, we know that energy is represented by the units of joules, and that will be also the case in this case of a light energy. We can see that while the energy of a single photon is an incredibly small one, having enormous amounts of photons can add up to a decent energy which can be used for illuminating our real world or virtually also our scenes in computer graphics. The light energy as such is carried through photons, and these photons are discrete particles. So measuring the energy through some is meaningful, but they often would come with slightly different wavelengths. Each particle will have a slightly different wavelength. And therefore, it makes sense to represent a light energy as an energy over a certain interval. Like, for example, here, the interval between 500 and 600 nanometers, which then results into an energy of a certain amount of joules, which is the unit of energy. If we will look into this interval between 500 and 600 nanometers, we will find several areas where there will be simply no photons of that wavelength represented and will not contribute to the overall energy. In fact, if we look at it on as a segment of real numbers, then the probability that there will be a photon exactly of a particular wavelength is equal to 0. So while this is not the case for the interval, for a singular real value, this would be the case. And if we will be shrinking and shrinking our intervals, there will become at some point intervals where there will be no energy, and then there will be intervals which will have a very high energy because there would be a photon. And it will be very, the more we will be shrinking the intervals, the more it will be uneven. Therefore, we would prefer to have a certain measure which is a little bit more behaving in a more monotonic way, if you like. So therefore, we are defining, instead of the energy which would be measured at a particular wavelength, which would be an sort of an extensive quantity, we want to measure a density of a energy over a certain interval. So, and such an energy would be the spectral energy, as we call it, and this quantity is an intensive quantity. So we can see here that this intensive quantity here is defined as the energy over the interval divided by the size of the interval here. So this gives us the feeling of how dense and is this interval in terms of light energy. So with this, we will be having some kind of a rational definition of a quantity of energy, which is the spectral energy, and of all the related quantities we will be discussing in the following. How can we imagine this spectral energy? Well, it can be understood as if we would take some kind of a color filter, which is able to pass through values of energy of a certain wavelength with a certain interval of delta lambda. And we will be measuring this energy associated with that wavelength interval. And we can see this here as the expression, and we can see also that therefore the spectral energy will be a quantity which will be smaller than an energy over a certain interval, because it is sort of normalized over that interval, delta lambda. So this is the quantity spectral energy. If you remember from high school physics, when we are talking about energy, we often also talk about power. And here we are following the notion of a spectral power, where we are again having the spectral energy as the quantity over a certain interval of wavelengths lambda. The spectral power will be measured in watts, which is a measure of joule per second. So we are introducing a quantity which will define the rate of energy production. That's the power as defined in physics. So let's have a look at a particular example. Imagine that we would like to know how much energy is somehow represented by a light bulb which is having a power of 100 watts. Well, we can have a look at the actual energy of one such a photon. Here we are taking an average value of the photon will be 500 nanometers in wavelength. And you remember the equation from the previous slides where we have the speed of light and the wavelength. So if we are performing this division, we will find out that the frequency is very high frequency, and with the Planck's constant, we will, if we multiply that, we will realize that in order to have something like 100 watts, we will need something like 10 by power of 20 photons per second to be emitted from such a light bulb. So this is an enormous number of photons which have to be emitted from a light bulb every second. The spectral power, as we denoted by this phi, is the spectral energy divided by some interval of time. And if we are putting the equation of which we learned on the previous slide, then we have our spectral power defined as our energy divided by the wavelength interval and also multiplied with the over the time. The next quantity we will be describing is the spectral irradiance. Irradiance is a quantity which defines how much of light hits a small surface area. So it is an entity which it is a quantity which sort of measures how much light has been concentrated on a small patch of a surface. It can be defined as the power divided by that certain area. And if we further expand this equation, we can see that the energy is divided by the interval of wavelength, interval of time, and an interval of area. So this defines the spectral irradiance, which is the light if we have a certain small patch of light. So how much is the light coming to this area over a certain time? So the orientation of the photons is towards that patch. if we would like to learn about another quantity, how much of the energy is leaving a certain patch, that is not the irradiance, that is called the radiant excidence, which is sort of the complementary to the irradiance. Now let's have a look at the central quantity of radiometry. It will be the spectral radiance, and the reason why it is a central measure is because through this measure, which we can actually measure with physical devices, we can derive all the other quantities. So here, in this case, the radiance is similar to irradiance, but it measures how much light is coming from a specific direction and through a specific solid angle interval, and hits a small surface area, as we had it already before. So our radiance, as defined here by L, is our irradiance divided by a small solid angle interval. And if we expand it, we can see that the energy is again divided by the wavelength as before, by the time interval, by the area interval, and by the solid angle interval. As you can imagine, if we are observing the radiance from all the solid angles in a hemisphere, we can obtain information over the overall irradiance. The radiance has an interesting property. It does not really depend on the distance from a surface because if imagine that you have a certain patch of a rectangle which is emitting constant light over its entire area. And if we are measuring the radiance, which is going through this small spherical angle onto a small area, then at the closer we are to this patch of emitting light, the smaller is this circle, which is sort of projected with our small conical shape, and therefore a smaller area is being sort of enabling the light go through this conical shape for measuring the radiance. If we are more far away, this circle is larger, but at the same time, the distance is scaling it in the same way so that the overall radiance becomes the same. The radiance is the intensity of radiance is decreasing with the distance squared, and the area is also increasing with the squared distance. So overall, we will have the same radiance quantity independent of how far we are from that light emitting patch. Now, if we are measuring the radiance on a certain surface, we can see that while previously we have been measuring the radiance over this small little solid angle opening, if we are measuring it at a surface at a certain incidence angle theta, then this area will be becoming bigger, larger, because it's a projected area which will form an ellipse, and it will scale the area of the projection. In order to correct for that, to measure really how much is coming of the light energy through this small area delta RA, we need to scale this area by cosine theta. So with this cosine theta, which is cosine theta will be between 0 and 1, we will be having a smaller value in the denominator and overall a higher value of the entire fraction. So this scaling will then increase the overall value of our radiance. By this, we will secure that the incoming light energy will be properly measured. We keep in mind that we measure the energy now here in this area, and therefore we need to perform this scaling. We can define two different radiances, one which is called the surface radiance, which is the radiance of leaving light from a certain surface patch. So the S will be an radiance through a certain solid angle from a surface patch, while the field radiance is the radiance which is of the incoming light to a particular small surface area under a solid angle interval. Radiance is a central measure in radiometry because, first of all, we can measure it. We can actually construct a device similar to the illustrations from the previous slides, where we have a small solid angle opening which is allowing light to enter and to be measured at a particular location as an intensity over a certain time. And therefore, we can obtain the values through experiments. And the second reason why is it a central radiometric property is that it can be used for deriving all the other quantities which we have mentioned. So irradiance, for example, can be obtained from radiance, and you can intuitively understand, as already mentioned, that the irradiance can be obtained from the field radiance over all incoming vector directions k over the entire hemisphere. So with this formula, we can obtain the irradiance, and we can also reformulate the equation such that the solid angle will be decomposed into the two angles which are parametrizing a sphere or a hemisphere. And that are the theta and phi, which are parametrizing our unit sphere. The differential, the sigma, which is the solid angle, is equal to this formula, where we see that the sine theta is scaling the differentials of theta and phi. Now, if we put that into our equation and calculate the actual integral over the theta goes between 0 and pi half, and phi goes 0 and 2 pi, so we have the hemisphere, we will find out that the integral is equal to, if we have a constant irradiance from all incident directions, that the irradiance is which is the radiance times pi. And furthermore, you can imagine that we can perform this integration strategy further in order to obtain from the irradiance the power, the spectral power, and further the spectral energy. And this leads us to the notion of bidirectional reflectance distribution function, the BRDF, which is often used in photorealistic computer graphics. The BRDF is a function which characterizes, and it's obtained through measurements from radiometry, which characterizes how much is um, of light energy is being reflected from a certain direction on which is emitted from a small surface patch. So we would have an incident direction of the light and an outgoing direction of the light, and what is the probability for an incoming direction that how much of light energy will be emitted to the outgoing direction. And this can be measured for a particular material with a goniometer, which is a device that consists of a light source and the detector of the energy, and samples simply for various angles of outgoing light, how much of the light energy is reflected in that direction. And that characterizes then the particular material. So this is the real sort of physics-based on experiments type of computer graphics, which leads ultimately to photorealistic representations, which are indistinguishable from the real world. Our approximations are just some which we have been using so far, are just simplifications which are not physically based, but they result into reasonable visual outcome with reasonably low computational effort. In BRDF, what we are interested in is to capture an information of how much of the fraction of the energy is being reflected in a certain direction. This means that we want to remain independent of the strength of the light. Depending on how strong it is, this probability will be, of course, scaled. But what we are interested with the BRDF to have a sort of a light intensity independent measure of the light distribution. In order to have such intensity independent capture of the light distribution, what we have to do, we have to measure the overall irradiance of the light and then use it as a normalizing factor for a measure of the LS, which is the outgoing radiance, the surface radiance in a particular direction, outgoing direction, KO. And this information we store in this BRDF function, rho, which here it looks like has two parameters, which is the incoming direction and an outgoing direction. Well, if we parameterize it through spherical coordinates, then each of these vectors will have two values for theta and phi, and therefore this is really a function which is going from, which is a four-dimensional function going from R4 to R. And in case we are dealing with a so-called anisotropic material, which its rotation also depends on the behavior of the BRDF, on the probability of reflecting in a certain direction, then this will be a function of R5 to R. This leads us to another measure of the ratio of how much of an incoming light energy has been reflected back and how much has been sort of absorbed or how much energy has been transformed into other forms of energy. And this is described by the directional hemispherical reflectance. This measure is defined as the radiant excitance, which is the complement to the irradiance divided by the irradiance. So if we assume that there is no particular light generated at our surface, but only the light is being reflected, which is shining on our surface from a certain direction Ki, then our directional hemispherical reflectance is describing how, sort of, in some sense, efficient is the material in terms of reflecting the light energy. And this, of course, can be dependent on the angle of the incoming light direction. This example again shows us how central the measure of radiance is in radiometry. And we can see, for example, that the surface radiance is defined and using this formula. And you can remember it still from the previous slide where we were actually expressing it for the BRDF function, which was then expressed as a function between the surface radiance and the irradiance. So if we are slightly reformulating this formula, we can see that the surface radiance can be expressed this way. At the same time, our surface radiance can be expressed this way, where we have our radiant excitance and divided as the complement to the irradiance, divided by the solid angle and also scaled by this cosine term, as was the original definition of our radiance. But here we are defining it not through irradiance, but through the radiant excitance, because we are going the other direction. If we look at this, now we have here the property of the irradiance and also the quantity of the radiant excitance somehow forming an equation. So if we put them on one side, we can express this fraction, which is in fact the directional hemispherical reflectance, as from a certain one direction as the value of the BRDF and scaled by the solid angle and by the cosine theta of the outgoing direction. If we are interested in all outgoing directions, then we will obtain the directional hemispherical reflectance through the integral over all outgoing directions, vectors KO, or the parametrization of the sphere through theta outgoing and phi outgoing. Now let's use this for defining and behavior of an ideal diffuse BRDF. Ideal diffuse BRDF is a BRDF which doesn't have any energy dissipation, so what is incoming energy will be also reflected, and it will be reflected with perfect probability, uniform probability in all outgoing directions. This means that for our value BRDF given a certain outgoing direction and incoming direction, we will always have just a constant value C. And if we integrate this over the entire hemisphere of outgoing directions, we will end up with the pi c, which will be the directional hemispherical reflectance. Now, if we are dealing with the ideal diffuse BRTF, this means that the directional hemispherical reflectance will be equal to 1, because there is the fraction between the radiant excitance and the irradiance those are equal. Therefore, the value of our BRDF is constant and is equal to, in every incoming and outgoing direction, is equal to 1 divided by pi. Now, if we will not have an ideal diffuse BRDF, but just a diffuse BRDF where a certain amount of energy will be lost, then we can scale it by, so the directional hemispherical reflectance will be equal to R, then our BRDF function will be R divided by pi. And with this, we will have it for all the incoming and outgoing directions as defined by the perfectly diffuse BRDF. Being equipped with the previous formulations of relationships between the quantities, we can already observe that the expression for an irradiance is the field radiance scaled by the cosine of the incoming direction and the size of the solid angle. This is just a reformulation where we were previously expressing the radiance, spectral radiance, through the irradiance, which was then divided by the cosine term and by the solid angle. So this reformulation, if we put it into the expression of our BRDF, we will observe that we can express the BRDF by the incoming and outgoing radiances. So in other words, the surface radiance and the field radiance. And now, if we again reformulate this equation so that we are expressing the surface radiance through this equation, then we will have for one incoming direction, we will have the following formula expressing us the outgoing radiance. Now, if we want to again obtain the surface radiance from all where the surface radiance is caused by incoming radiance, the field radiance from all incoming directions, then we again sum it up through an integral where we have our BRDF function, as we have discussed it before, multiplied by the field radiance of the incoming direction and scaled by the angle of incidence and the solid angle. It is very similar to what we have here, but it is just an integration over all incoming directions. And this equation, which we see here, is the central equation in photorealistic computer graphics. This is the rendering equation. Such equation characterizes the light transport between the incoming light and the outgoing light. Sometimes, especially in closed environments, we would like to express the radiance, which is the surface radiance is becoming a field radiance for another surface element. So here is the transport between different surfaces of our scene. We can see it here on the following drawing, where we see the prime surface area and of the x prime and the surface area of x. We can see that the incoming direction of, of light energy is actually coming from the x prime here, which means that our field radiance for the point x here, so LFKI, is actually the surface radiance of the other surface point. So this is the LS outgoing radiance in the direction minus KI. Now, we can also calculate what is the solid angle interval by just measuring what is the sort of a projection of our small a prime area and scale it by the distance between the surface point x and the surface point x prime squared. Because with this, we are basically creating a very long and thin cone, which characterizes us what is the, and this characterizes us what is the solid angle of such a cone. So if we now replace the solid angle with this formulation here, we can now express one surface radiance at a particular position and a particular outgoing direction through a surface radiance of another point. So you can see here this LS expressed here is the surface radiance at the point x prime towards the direction which is the Ki, which is equal to x minus x prime. So this is our surface radiance at the point x prime. And we are further keeping our term of the BRDF. We have also our terms for the cosine incoming theta direction. And then we have these two terms and this term coming from this equation. This is the replacement for our solid angle. So here is the cosine theta prime, which is the angle between the normal at the surface point x prime, and the theta is the direction, is the angle between the normal at that position and the direction of the outgoing surface radiance towards our point x. So, and we are left here with one more term. There's one more term here, which characterizes as the entire light transport between the two surface points, is this term V. I have to delete some parts here so that you can see it. This point V, this term V is a simple visibility term, and that is defined as 1 if the point X sees the point x prime directly and is equal to 0 if there is an occluder in between, so that this point x prime cannot be seen from the point x, meaning that there is not a direct connection between these two surfaces and there is no direct interaction of the light transport. Everything what we have discussed so far were objective physical quantities which are measurable, and they relate to ratios which ultimately relate to light energy originating from photons. And that is the field of radiometry, which is associated with the quantities we have described. But this way of viewing the light energy doesn't really include the human. We know that we are having in our retina of our eyes certain neurons or receptors which are processing the light energy exposure, and they are differently behaving or being excited based on the incoming light energy. And this excitation is definitely not linear. There are various aspects which are for a separate lecture or lecture series, but what we need to understand is that there is a certain function of how much we as humans are sensitive to various wavelengths. So for example, as we can see here, we can see a function termed the luminous efficiency function, which shows us the amount of sensitivity to particular wavelengths. So we know that anything below the ultraviolet light or infrared light and ultraviolet light is not visible. So here in this area, we will have an area of light which we do not see. This is the ultraviolet. And here will be the infrared area, which we will also not be able to perceive as a visible light. And in between, we can perceive visible light. So within this interval, we can see and perceive light, but also not at in a uniform way. So we are most sensitive to wavelengths around 555 nanometers, and towards the borders of the visible light, the sensitivity is decreasing. So therefore, it is important to be able to express the objective radiometric quantities into more subjective measures, which are the photometric quantities, which are characterizing our human perception of light. This can be there could be identical quantities defined in the photometry, but we need to be able to somehow convert one quantity, the radiometric quantity, into the photometric quantity, and the other way around. And therefore, we have here this useful function, which, given us any spectral radiometric quantity for a certain, associated with a certain wavelength, and scaled by the sensitivity function, luminous efficiency function, depicted here, we will be able to obtain the corresponding photometric quantity. And we can see here that we are now integrating over various wavelengths so that we can apply for any radiometric quantity for a particular wavelength this scaling factor coming from this luminous efficiency function. Once we obtain the sum, which will then characterize the overall photometric quantity, we are scaling it further with this scaling factor because the photometry and the radiometry somehow developed independently, and the two measures need to be put into a certain consistency. Therefore, there is this scaling factor. The photometric quantity, which is equivalent with the power, will be, and described by watts as units, is the lumens, which is the photometric quantity of perceived power. The situation is further more complicated with an eye adaptation. So the photometric quantities are calculated based on not taking into account the adaptation of the eye. This way, we can express, for example, the luminance, which is a quantity from a photometry and is somehow equivalent to the radiance. Luminance describes how something is bright, independent of eye adaptation, but dependent on the luminous efficiency function. Therefore, our luminance can be calculated as an integral of our radiance, which is for a given wavelength, and scaled by the luminous efficiency function, and outside the range of visible spectrum, this will be anyways 0, and we can that way from the radiance obtain the luminance. Luminance is often defined through L, but here keep in mind that we were using L for the radiance, and it would be of no help if we will be mixing up the radiance and the luminance, so the radiometric and the photometric quantities. The corresponding measure to watts, to power, are the lumens, which are expressing the relative perceivable light output. And the luminance, its measure, is the lumens by the area and the solid angle. We will be talking about the luminance when we will be discussing the color, which is somehow the intensity of which is if the color is decomposed into its chromatic and its achromatic intensity components. And that will be all for today about the light. We had a short view into radiometry and even shorter into photometry to understand the physics quantities and their interrelationships so that we can use them on the following lectures on color and on global illumination and reflection models. Thank you very much for your attention.